Hey guys, so I'm back with another video, and this time I have a goal that is not going to exceed 15 minutes. I know that the last couple have been really long. I don't blame you if you were not able to sit through them. This is, I think, part of the learning process is learning how to teach things concisely. So I'm going to attempt to do a little bit of a better job this time. But yeah, I'll kind of cut myself off once we get to 15 minutes. So today it shouldn't actually be as in-depth because I'm just going to do some of the problems that I've been doing from problem set 1.3 that I kind of went over with Dr. Prudhomme, some of the things that I had questions on, some of the things that I figured out. And then next week will probably be a 1.4 note kind of lesson. So I'll just jump right in the interest of time. So we start out with this equation, x1. Okay, so this is the equation that they give us. So you've got x times vector 1 plus y times vector 2 plus z times vector 3 equals vector 4. So you've got, and the way they sort of draw it, you've got this kind of geometric thing going on here. Those three are the vectors that are on the left side of the equation. And this is vector 4. V1, V2, V3, V4. So they want you to show geometrically at least two solutions of this equation right here. So the way I went about doing this is I'm only going to show one because I think once you get the idea, you get the idea. So what I think worked best, and actually I do this wrong, it should be shorter. Yes, and this one should also be shorter. So the thing that I showed you before in past problems is that when you've got something like this, basically, you know, you're figuring out how much you have to multiply x by, or multiply these vectors by, right? So what I figured out here is that you've got three vectors. So you can take two of them and make a solution out of those two, and then the third one can be multiplied by 0. So that's how you can kind of figure this out. So like the one that I'm going to show, okay, so here's what you've got. If you multiply this vector so that it comes up to this point on the y-axis, and then you multiply this vector so that it moves over to this point on the x-axis, then that allows these two to resolve into this vector, right? So that's kind of how you can do that one. And see here, you know, you show only these two are actually making are actually resolving into this vector, but for this third vector right here, the z, or this is vector 2, so the y, it's multiplied by 0, so the y here is 0, right? So x is a number, z is a number, y is 0, and that is one of the solutions, and that just kind of shows one of the solutions. But there's a second part to this equation, which is explaining how it's true that this equation has infinite solutions, and you do this with algebra, not with geometrically. So the way that I went about this is I used the previous definitions that we have for matrix algebra. So what I know is that when we talked about the column method for solving AX equals B, this is kind of the reverse column method. Because what we can do here is we can extract out, we can say these three vectors are three columns of a matrix. We've got V1, V2, V3, up, down, up, down, up, down. And then you multiply that times, you've got three components of a vector here once you put them together, x, y, z, x, y, z equals V4. Now, the question that I've not answered is how many rows are there here? Well, we know these lines, they're lines, right? Which means that they're all in the XY plane, which means that there are going to be two rows. So the last thing that we can show, got V1, we've got one here, V2, something here, something there, V3, something there, times X, Y, Z equals V4, something there. Once we've gotten to that point, what we can say is that right here, if we would multiply these two together, we've got 2 times 3, 3 times 1. Or, sorry, ignore that. Ignore what I just said. We're not going to multiply them together, but we know, right? So here is 2 rows, 3 columns. What does that mean? N is less than M. So based on our rules of solutions, what can we say here? That means the solutions are either going to be infinite or 0. So let's look at why that's true. I'll remind us in case we forgot. Say we've got like A, B, C, D, E, F. So we've got 3 variables here. Let's say that we are only going to solve for these 2, right? Which means that we're going to have free variables left over. Which means that these free variables are going to have to be infinite, right? Because anytime that we have free variables left over in an equation, that means that they're going to be infinite, right? Now, of course, there's a possibility here that this could all turn out to be 0, right? That this could X out and become 0, 0, 0. But in that case, we have an option. Either it's still infinite because the other side also equals 0, or like I said, it's inconsistent because the other side equals like another number, say 4. But either way, it's going to be either infinite or inconsistent. But we know that it can't be inconsistent because we just drew out 2 solutions. So that's how we prove that this equation has to be infinite. So that was our first problem. Super quick, hopefully. Next problem. This one should not be as involved. So this one's kind of another proving matrix, proving problem. A lot of the problems in this problem set were about kind of proving things true. So we've got a 4x4 matrix. Vector B and vector C are 2 vectors in the subspace of R, right? The 4x4 matrix. So we're trying to find the number of solutions for A times vector X equals C. What we know is A times vector X equals B is inconsistent. And the book wants us to show what are the options for solutions, or what are the options here for this equation based on the fact that we know that this is inconsistent. So the way that I set this up is I've got a 4x4 matrix. I've got X, that's also 4x4, equals B. So here's what we've got. A1 plus A2 plus B3 plus B. Well, actually, I'll do these in proper notation just for sake of consistency. So that'd be 1, 1, 1, 2, 1, 3, 1, 4, A2, 1, A2, 2, A2, 3, A2, 4, A3, 1, A3, 2, A3, 3, A3, 4, and A4, 1, A4, 2, A4, 3, A4, 4. We've got X, Y, X1, X2, X3, X4 equals B1, B2, B3, B4. This is what we've got here, right? So we know that this system ends up being inconsistent. So that means that one of these lines, at least one of these rows, became 0, 0, 0, 0 equals a number B, right? It could have been more than 0. been more than one row, but at least one has to, because we've got to have the thing where we've got 0 equaling a number that is not 0 for it to be inconsistent, right? So we know that, this number here was not 0. Now, if we extrapolate this into A times X equals C, let's change this here. C1, C2, C3, C4. Nothing on this side has changed, which means the same number of rows are still 0 as they were on the last one. What has changed is that we don't know, because we don't know if it's inconsistent or not. We don't know if the answer's on this side, like if the row that's 0, if the other side equals 0 or a different number. We don't know that, right? But we do know that we have at least one row that's going to equal 0, which means that we have two options. It's infinite or it's none. So that is the answer to this one. Hopefully you're kind of starting to see that you just kind of take the rules that we learned in the last section and you just kind of apply them here and use sort of that geometrical proof mindset. Okay. Here is the next one. This one's actually pretty simple, so should not be too bad. We actually only have 2 more left, including this one. So we've got a problem that says in all real numbers of m, we define vector e of I to equal 0, 0, 0, dot, 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 1, dot, 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 0. This one, the ith component of the vector. They want to know if A equals an n times m matrix, A of the ith component of vector E is what? So here's what we need to think about. If we're taking a vector and we're multiplying it, if we're taking a matrix and we're multiplying it by this vector, that means that one column is going to stay the same, like the coefficients are just going to be themselves, and all of the other columns are going to be 0. So in other words, the whole matrix will get canceled out except for one column, which will be isolated to just be its own coefficients, right? So the way that we can draw this is if we've got the REF form, like the reduced row echelon form of an n times m matrix. We have 0 plus 0, dot, 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 plus 1 times, let's say, a coefficient A plus dot, 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 0 for however long that goes on. 0 plus 0, dot, 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 plus 1 times B plus dot, 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 0 forever, however long that goes on. And then for however many rows there are of this, right? So we can't figure out anything more than this, but basically what this is saying is that this is a good fact to know, that if you've got a vector where everything is 0 except for one number, which is just 1, it's going to isolate out one column that's just going to be the coefficients. So that one's pretty simple. I just wanted to kind of show the notation for it. The last one is, in my opinion, the most important for me personally, because it's the one that really baffled me. And I had to, this was the one that Dr. Prudhomme and I spent most of our time discussing this week. And I completely understand it now. My main question is recognizing this kind of thing when it comes up later, because it was definitely sort of a more creative kind of thinking problem. But the book gives us this little drawing here. Okay, so basically what it wants you to know is that you've got this equation AX equals B. This vector is the X that it's talking about here. These are the solutions of AX vector X equals a 0 vector, which is, in other words, a thing where you just got like 0, 0, 0 down the line for however number of components there are. It wants you to draw the line that represents all the solutions to this. So there's a really sort of creative way of thinking about this that was the answer, which is that you know that A times x1 equals b. We were given that, right? But we also know that there are going to be other vectors that A can be multiplied by to get B, right? Like there are going to be other vectors that can be multiplied to get a line of a solution, right? So say we've got A vector x2 equals B as well. Here's what we can extrapolate out. A vector x minus A vector x2 equals B minus B, right? That makes sense based on what we know about solutions, right? So then we'd pull out A times x1 minus A vector x2 equals vector 0. This should look familiar. Vector 0, right? So basically, we know that for vector 0, it equals A times x1, vector x1 minus vector x2. Here's what we should know about vector multiplication, vector subtraction when we're doing it geometrically. Here's something you have to know first. So say we've got these two vectors. We've got v1 and v2. If you subtract them, it's this line, okay? So that's what we should know going into this. Now that we know that, let's take this other vector that we're talking about, x2. And of course, it has to be connected here as well, so that it will be a solution. So this is x2. If you subtract these two things, it's going to be a dotted line right there, right? Sorry. Which means that the solutions for ax equals b are going to be parallel to the solutions for ax equals a. And the reason it must be parallel is because, so one thing we should know about vectors, and I might have already brought this up, like vector position doesn't matter. We can move this as long as it's still in this parallel, or as long as it's still this vector, we can move it all around, up, down, whatever, right? So which means that this vector is the same as this vector, right? Like we can move it down and it can fit over top of this vector, and that has to be necessary because x2 minus x1 has to equal, or A times x2 minus x1 has to equal the 0 vector, right? So these two have to be parallel. So that's how we figure out these are the solutions for A, x1 equals B. So I definitely understood this after meeting with Dr. Prudhomme. I think my big question going forward as we hit problems like these are just really practicing that sort of creative process of thinking about math. And I think that that's something that will have to be built up over time, and that will get easier as I get more comfortable with the material. But that is all I have for y'all today. Let's see, how long did I end up going? I think I actually made it in 15 or 20 minutes. So yay, that's really good. Yeah, I hope you enjoyed the video. Hopefully it was less daunting than the other one. I will see you next week.